Well, hello there again. Welcome to another physics tutorial brought to you by O3 Schools JAMB app. O3 Schools JAMB app, the best, the only app you require preparing for JAMB, has all your subjects, plenty of questions, and plenty of other features to help you as you prepare for your examination. All you have to do is activate your app, which costs the sum of 2,500 naira. And yes, so I know that there are some fraudsters out there where you try to activate and it doesn't work. However, you can trust this app. Just follow the steps as outlined in your app, and you shall receive your activation pin and subsequently be able to make use of your app to gain access to all the features. And with that, let's get to this lesson. In this case, we shall be looking at heat energy. Now, most of us we know heat, but we do not quite have a definition for heat. We do know that heat causes change in temperature, and as such, we can define temperature easily. Again, the layman's terms for temperature, hotness or coldness of a body. But then, what is this heat? Now, first thing you must know is that heat is a form of energy, also referred to as thermal energy. And the special thing about this energy that it always travels in one form, from the hotter body to the colder body. So heat is basically a form of energy which travels from one object to another based on temperature difference. The heat always tries to go from the hot to the cold until something known as thermal equilibrium is reached. Thermal equilibrium. This may sound a little bit fancy. What this simply means is that heat will always flow until the temperature of the two bodies becomes the same. Once that happens, heat no longer has any idea where to go because it wants to go from hot to cold. But if say the both bodies are now at 50 degrees Celsius, then neither is hot compared to the other, and neither is cold. As a result, heat transfer stops, and that's what we call thermal equilibrium. So it always flows until thermal equilibrium is achieved. Say you are trying to make tea, and you think this water is too hot. What can you do? You can mix this water with cold water to get what we like to call warm water. Simply, in that situation, the hot water is losing some of its energy to the cold water. So the cold water rises in temperature, the hot water drops in temperature until a moment where both temperatures becomes the same. You can simply assist that change by certain steps, like turning your water to make it change faster. However, that change is bound to happen. Now, you must have noticed that when you apply heat to different substances, the temperature doesn't always rise the same amount for the same heat. For example, applying the same heat, or in the easiest way, putting two different spoons in a pot filled with water, a metal spoon, a rubber spoon. The metal spoon obviously gets hotter much faster than the rubber spoon. And while yes, we know this is because metal is a better conductor and rubber is an insulator. However, mathematically, if you want to quantify this difference, this ability, we then have to look at something known as specific heat capacity. This specific heat capacity. That is our way of quantifying this change in temperature. Now, what specific heat capacity? Just keep in mind, in anything you do in physics that has specific attached to it, they always mean per unit mass. So if there's a specific, there's usually a general name for it. For example, if you're having specific heat capacity, then there's also going to be heat capacity. Specific heat capacity has to do with just 1 kilogram of this material, while heat capacity has to do with the whole, the entire material. So let's see, what is specific heat capacity? This is what measures the change in temperature of a unit mass of a substance when subjected to the same amount of heat in the same amount of time. Quite simply, mathematically speaking, heat Q equals to mc change in theta, where this Q is the heat being supplied, m is the mass, change in theta here refers obviously to change in temperature, while C is the specific heat capacity. The specific heat capacity. And its SI unit is joule per kilogram per Kelvin. It's that simple. Now, obviously, the material with a bigger specific heat capacity will actually undergo a smaller change in temperature when subjected to the same heat and the same mass as when a material having a small specific heat capacity has the same heat with that same mass. Like I said at the beginning, if there is going to be a specific, there will be a general. And in this case, our general is simply called heat capacity, which actually refers to the change in temperature for the entire body. And that's quantified by saying heat capacity beta Q equals to mc. So we use small q for heat capacity and big Q for the specific. Now, if small q presents mc, as you can see here, that must mean that big Q heat equals to small q heat capacity times change in temperature. Now, those are the first two formulas you must know while dealing with this topic. What then is next? What else do we need to know? One of the most important things you must know is that from the law of conservation of energy, energy is neither created nor destroyed, but transformed from one form to another. Therefore, if there's going to be heat energy, where is the heat coming from? This heat can come from a myriad of sources. An electric cooker, in which case the heat is coming from ITV, like you know if you've done your electric circuits, or this heat comes from even yet another body, a hot body attached to a cold body. This hot body will lose temperature and temperature will drop, while the colder body will gain temperature, which will then rise until both temperatures become equal, which then indicates that if for a closed system, for a closed system, heat loss must be equal to heat gained. Now we have to say the system was closed to indicate that this energy is not escaping. No, instead, as long as all the energy remains within a particular system, if one object is losing heat, that heat isn't disappearing, it's being gained by another object. One more time, if I also take this as a bucket, so yeah, let's say we had water inside it. If I put several blocks of ice in this water, so where these blocks of ice are at a lower temperature than the liquid water. As you are aware, obviously, blocks of ice begin to melt. They are gained heat required to melt. And at the same time, my water begins to get cold. And therefore, if this system was well lagged, or in other terms, if it was a closed system, then the heat being lost by this water is not just disappearing, it's being transferred into the ice. And this is our initial gist that we need to know. Now, once we know this, we have to remember, what if there's a change of state? As you're aware, I just talked about ice. Ice melts, and water can also boil. In those situations, is our calculation exactly the same? Not quite. In those situations, we have to introduce a brand new concept, and this concept is known as latent heat. Latent indicates hidden. Your latent heat is therefore a fancy way of saying hidden heat. How can heat be hidden? Is because the obvious way by which we know there is heat is by temperature change. Therefore, if heat is being supplied, although temperature is changing, then it appears obviously that that heat is hidden. And that's exactly what goes on during change of state. Like I said, latent heat always has to do with the change of state. And as such, there are two forms of latent heat. There is latent heat of fusion, which has to do with melting, and there's also the latent heat of vaporization, which in this case has to do with boiling. So you're either melting, which is going from solid to liquid, or liquid to solid, or there's vaporization, which has to do with either going from liquid to gas or from gas to liquid. Obviously, if you are going from liquid to gas, you are gaining this latency to vaporization. While you're going from gas to liquid, you are losing this heat of vaporization. Now, in this situation, rather than using MC change in theta, we should note that there's no change in theta, and therefore the formula is simply that the heat in this situation is mass times latent heat of fusion, as if this thing is melting, or it can be mass times latent heat of vaporization, in which you use it when this thing is boiling. And now, generally, these are the formulas we shall use in this topic when calculating for heat transfer. Now, you may see this in your exam. A simple way in which everything can be expressed is making use of a single graph. How? You have the vertical, as with any other graph, there's a horizontal component. This vertical will measure change in temperature. So, and this horizontal, sorry, I'll try to do with time. So let's say we start with eyes. Eyes, obviously, is 0 at minus 30 degrees Celsius. Now, if I have eyes and I begin to apply heat, the temperature of my eyes must increase. And in this situation, we are in the solid phase. Temperature of the eyes will increase until it gets to its melting point, which is 0. Then my eyes, the temperature remains constant. And then what happens? Every single heat you begin to apply, rather than increase this temperature or take it higher, it then begins to change the state. Implying that if I have a block of ice, the temperature of this ice remains constant until my ice has completely melted. No energy will then be used to change temperature. Instead, it's being used to change state. So my ice remains at this temperature until it has completely melted. That's the line on my graph. And then, once my ice has melted, I have liquid water. And again, temperature begins to rise. It does this in the liquid state until one more time it gets to the boiling point, 100 degrees Celsius. And then what does it do? It no longer raises the temperature, and just like before, it has to wait until all my liquid water has boiled. Once all my water has finally boiled, only then, when I now have steam, and this guy then again increase in temperature. As you can see, we have 5 zones. This is in the gaseous, sorry, this is in the solid phase. This is the liquid, and this is the gas. This is ice, this is liquid water, this is steam. Now, at this point, we're having melting, and in melting, we deal with latent heat of fusion. While at this stage, we are having boiling, and in boiling, we deal with latent heat of vaporization. Then, during this gaseous stage, this will be MC change in theta. But the C here must be the C of the gaseous stage. During this stage, we have also MC change in theta. But one more time, the C here must be the C of the liquid stage. While here and usual MC change in theta, and the C must be the C of the solid phase. You see, in any question you have, no matter how difficult this question may appear to be, especially questions in WAEC are usually longer, more difficult than the ones in JAMB because you have more time to solve. So in those cases, they may give you one that even comprises of all 5 stages. In which case, meaning you have to solve from here. I have to solve going from solid to the melting point. You have to solve for the melting. Then, as a liquid, going to the boiling point. You have to solve for the boiling, and then you can solve for the gas increasing in temperature. But typically in JAMB, you will either solve for single stages, or you may solve for 2 stages or 3 stages. You'd hardly ever see a question in JAMB which makes use of all these stages. And this is for the calculation aspect, to which we shall turn very, very soon and solve some questions using our O3 Schools JAMB app. However, before we go there are some theoretical knowledge which we have to know. And for example, if we have a solid stage here, the liquid, and the gas stage. If I'm going from a solid and turning into a liquid, that process, as we are aware, is known as melting. If I'm going from a liquid and turning into a solid, then that is known as freezing. On the other hand, if I'm going from a liquid and turning into a gas, from liquid to gas, that is boiling. Now, that name for boiling is vaporization. Now, some of you might be saying, what about evaporation? I shall explain that subsequently. But you should also know that gas to liquid is known as condensation. While any material that can jump from solid straight to gas, that material is experiencing sublimation. Now, if you're going from gas straight to solid, there are several names for that. Some people will just call it sublimation. Some people call it reverse sublimation, and some may even call it deposition. It's your objective, whichever one you see, you can take as your answer. Now, as I was saying, some of us will then bring up evaporation as compared to vaporization. Now, what are the differences? Please note. Evaporation is not quite vaporization. Yes, both of them involve change of state from liquid to gas. So, what are the differences? One, vaporization occurs at a fixed temperature known as boiling point, while evaporation can actually occur at any temperature at all. Evaporation can occur. Then also, vaporization is unaffected by factors such as wind, whereas evaporation is affected by such factors. Vaporization is unaffected by the surface area, for example, while evaporation is affected by surface area. The bigger the surface area, the faster the rate of evaporation. A concept you should be aware with, like when you dry your clothes outside. The water from your clothes, eventually, yes, when you dry your clothes get dry. When the water leaves the clothes. But when the water leaves the clothes, by what process does this occur? Does water actually boil off your clothes? You touch your clothes and see your clothes at 100 degrees Celsius instead of boiling water? No, it doesn't get that high. That is simply evaporation, not vaporization. So as you see, those are the key differences between boiling, which is also vaporization, and evaporation. Then there are several factors that can affect this boiling point that we just looked at. Boiling point can be affected by either impurities or pressure. Please note, the higher the pressure, the lower the boiling point. If you drop pressure, it's easier to boil, which is why your pressure cookers are able to cook your food faster. While impurities increase boiling point. You have impurities, your substance takes longer or more heat to boil. While if you are to look at it in the sense of melting point, it's also affected by those two factors, yes. Impurities, however, raise your melting point such that it is easier to melt at normal room temperature than it would have been. So raise the melting point, while pressure also affects it. There is a particular process known as regulation. Regulation simply occurs when you take a block piece and use a thin piece of wire and apply force on that wire downwards. Now, obviously, as this wire is pushing against it, it's applying pressure to this place, and therefore that will make that surface at which is applying pressure, that surface actually melts first. But as soon as this wire passes through, the pressure is gone from that surface. So if this wire is still at the temperature it should have been, or rather if this metal or this ice is at that temperature, then this ice can try to freeze back above your wire. It's possible to have wire within ice, whereas this ice did not form with the wire there initially. So you can cut through this wire, through this ice block with that wire, and this ice block will still actually at the end of the day remain in one solid piece. That is what is known as regulation. So these are tiny questions that can be asked during your exams on the theoretical aspect. And if these have been understood, we shall now go to our old three schools JAMB app, from which we shall answer several questions having to do with this topic. So let's see. Opening our old three schools JAMB app. Our first question comes from the year 2004. Question number 39. We have got questions now. 2004, question 39. A 50 watt electric heater. A 50 watts. What do we measure in watts? Obviously, power. Implying that the power is 50 watts. So, this 50 watt electric heater is used to heat a metal block of mass 5 kg. Next thing I know is my mass as 5 kilograms. If in 10 minutes, more information, time is 10 minutes. We know we cannot solve in minutes, we solve in seconds. So times 60 should give me 600 seconds. If in 10 minutes, a temperature rise of 12 degrees Celsius is achieved. My change in temperature was 12 degrees Celsius, which is the same thing as 12 Kelvin. So whenever you have temperature rise, there's no need to convert. Then we are being asked to find the specific heat capacity of the metal. Now, we have electric heater, and as you are aware, we said heat equals to MC change in theta. Where is this heat coming from? Electric heater. What's the energy of this heater? Power times time equals MC change in theta. So you want to find C. C to stand alone means I'll divide by M and change the theta. M and change the theta. So instantly I know that my specific capacity C must be PT over M change in theta. Therefore, I know that my P, my power, is 50 watts. So that's why the 50 there times my time. My time is 600 all over the mass. The mass is 5. And change the theta is 12. So we have to do some simple multiplication and division. If you can't, obviously, you can always do this with your head. 5 here is 1, 5 into 5 here is 10, and 12 here is 1, 12 into 60 is 5. So I'm left with 10 times 50, which is 500. And as I said, the SI unit for specific heat capacity is joules per kilogram per Kelvin, which indicates that my answer is option A. You can see these are very simple. Well, okay, now a second question, example 2. This is from the year 2003, question 25. Also using our old three schools JAMB app. The search feature is actually quite wonderful, I must tell you. A 2000 watts electric heater. Again, we have power. 2000 watts is used to heat a metal object of mass 5 kg. The mass is 5 kilograms. Initially at 10 degrees Celsius. Initially at 10 degrees Celsius. Let's call this theta initial 10 degrees Celsius. If a temperature rise of 30 degrees Celsius, now the temperature rise is 30. You're getting that the change in temperature is instantly 30, which means I'm no longer having to do with this initial temperature. If you were to tell me I have initial temperature and I have a final temperature, then my temperature rise will be the final minus the initial. But this question they told us straight away that the temperature rise is 30. So I don't even do anything with this my initial temperature. So I know my temperature rise, and if the temperature rise is obtained after 10 minutes, the time is 10 minutes, which again we multiply by 60 is 600 seconds. We have to find the heat capacity for the material. I keep in mind now, we're finding heat capacity, not specific heat capacity. Try to avoid making the mistake of looking for specific when they did not ask you to. And just like before, if I'm finding heat capacity, I assume that my heat Q equals Q change in theta. But again, just like before, my heat is coming from somewhere, which is power times time. What's the Q change in theta? And to make Q stand alone so I can find it, implies that Q must be PT over change in theta. And P is 2000, T is 600 over change in theta, which is 30. So 0 can take care of 0. 3 1, 3 into 60 is 20. And therefore, 2000 times 20, 2 times 2 is 4. Then I have 4 zeros. That's the fourth one, and this is going to be in joule per Kelvin. However, if I look at my options, I realize that in standard form, well, obviously, if you do not have energy, you could simply know that option B is the one having 4 as the first number. That must be my answer. But if you like, you can remember 1, 2, 3, 4. That's 4 times 10 to the power 4. I noticed they use joule per degree Celsius in theirs, which again, like I said, it doesn't really matter in this case. It doesn't change the temperature. The change in Kelvin and the change in Celsius are usually the same. Then, just for a fun theoretical question, this is from the year 2000, question 26. 18 wire with heavy weights attached to both ends hung over a block of ice resting on 2 supports. If the wire cuts through the ice block while the block remains solid behind the wire, the process is called. I don't have to stress yourself. We just talked about it. This process is known as regulation, and that is option D. See, these are all really, really simple. Now, the next question we'll have is yet another theoretical one. Or rather, sorry, this one is solving analytical calculations. Heat is supplied to a test tube containing 100 grams of ice. So the mass is 100 grams. Before we look at this, normally we would convert this gram from grams to kilogram because we know actually it is kilogram. But if you look at the bracket at the end of the question, we're told latent heat of fusion is 336 joule per gram, indicating that they are solving in grams. So I ought to leave this my mass in grams. So please, you do not always have to convert. Look at your question, and your question requires these parameters in a certain value. Then you have to work with that value, like so. Then it has this 100 grams of ice at this melting point, and this ice melts completely in 1 minute. 1 minute, which we know is 60 seconds. That means asked, what's the power rating of the source of heat? I want to know the power, and that the latent heat of fusion of ice is 336 joule per gram. Now, in this case, rather than having a change in temperature, we are having a change of state. The ice is melting, which indicates automatically that my energy, my heat energy, is being used to melt, MLF. But we want to find the power rating. That is power times time equals to MLF. Again, to make P stand alone over T, P equals to MLF over T. The mass is 100. LF is 336 over 60. 0 can actually cancel 0. What else? Cancel is going to 336. 6 here, 1. 6 to 33 is 5. Remember that 3. And 6 into 36 is 6. That will give me 10 times 56, which is 560. We're solving for power, and that is going to be in watts. Look at my options. That is easily and clearly option C. Tracy, the steps are very, very simple and rudimentary. At which point, I think we shall take one more calculation question on this topic. to further improve our understanding. This one is from the year 1994, but this is question number 16 now. We've done 17, now we're doing 16. And this one states, when 100 gram of liquids L1, so let's say this is going to be mass 1, it has a mass of 100 gram, at 78 degrees Celsius. We shall say the initial temperature, I'll call it theta 1, I. Theta 1 here, the one indicates that I'm dealing with this first one, like M1, theta 1, go together, while the I here is to represent initial. So it was at 78 degrees Celsius. And then we are told that it mixed with X gram, so M2 will be X gram of liquid L2 at 50 degrees Celsius. So theta 2I is 50 degrees Celsius. The final temperature was 66 degrees Celsius. Now, like I said before, for thermal equilibrium, if two things mix, the final temperature is always in common. That means both 1 and 2 end up at the same final temperature. And that temperature was 66 degrees Celsius. And then we are told, given that the specific heat capacity of L2 is half that of L1, so C2 is half C1. Or if you prefer, you could cross multiply and therefore note that C1 times 1, which is C1, equals to 2C2. Because typically I know we prefer working with whole numbers than with fractions. Now, with all this information we seem to have on the board, what can we do to get this max M2? Again, very, very simple, really. First thing I need to know, if there's going to be heat transfer, the heat lost by one must be equal to the heat gained by the other. Now, since we have just two things here, one must be losing heat and one must be gaining heat. How do we identify? Looking over here, this was 78 degrees Celsius going down to 66. That's a loss of temperature. So this heat is reducing, which means the liquid 1 is losing heat, which from 78 to 66, while liquid 2, starting from 50 to 66, it is gaining heat. That means the heat is being lost by L1 because the heat being gained by L2. Now, how can I represent this heat being lost? I know that heat equals to MC change to theta. But since I know I'm dealing with L1, I'll say M1 C1 change to theta 1 equals to M2 C2 change in theta 2. Now, what's my M1? That's 100. Again, if you want to ask, why did I not move it from gram? Because I know X is in gram. And therefore, if I was to convert this to kilogram, this my answer will come out in kilogram. Then I have to convert it again back to gram. So instead, since I want to get X in gram, let me leave it in gram. Then C1. Once if I think C1 here, I know that C1 equals 2C2. I can have 2C2 appearing here. Then change in theta 1. Theta 1 went from 78 to 66. So that will be 78 minus 66. Always arrange these to give you a positive answer. And this should be equal to, I'm writing the equal to here because I've not have enough space on the board to stretch this out to the end. So equal to came down a bit. M2, which is X, times C2, which I can just put as C2, times its own change in temperature. It's going from 50 to 66. Therefore, change temperature should be 66 minus 50. Like I said, always write this out such a manner that you get a positive answer when you subtract. So 100 can multiply this 2 here. That is 200 C2 times 78 minus 66. That is 12 equals X times C2. Let's call that X C2 times 66 minus 50 is 16. Now, obviously, I want to get X. What can I do? And divide it by C2 divided by 16. So divided by C2 times 16. C2 cancel C2, 16 cancel 16. X must be C2 cancel C2. So I'm left now with just numbers and no letters. Let's say 4 into 16 is 4. 4 into 12 is 3. 4 into 4 is 1. 4 into 500 is, sorry, 4 into 200 is 50. So that'll give me 50 times 3. That is 150 grams. And so if I go back to our trusty O3 Schools JAMB app, then I see my options and I know that my answer must be option C, which is 150 grams. And so you see, we've answered several questions and we understand now the way this goes. Just to round up, we shall take a look at just one simple theoretical question and we shall call it quits on this topic of heat energy. Now, for this one, we have been asked, which of the following statements, which of the following statements give the true difference between evaporation and boiling? Remember, we explained this. Number one, evaporation occurs at all temperatures, while boiling occurs at a fixed temperature for a given pressure. Yes, we said that. Boiling only occurs at, as it is called, the boiling point, while evaporation can occur at any temperature. So we know one is correct. Keep that in mind. Two, evaporation is a surface phenomenon, while boiling is an interior phenomenon. Also, quite true. When boiling water, as you are aware, typically boiling starts from within the base inside your pot or your kettle, rising to the top. That's interior. Evaporation, on the other hand, starts from that simple surface. It focuses on that surface. So yes, two is correct. Then three, evaporation is affected by surface area while boiling is not. Again, also correct. That's the reason why you actually spread your clothes to dry. If you take the same clothes, like two the same material, to use made the same clothes that's the same size, put them in water, bring them both out at the same time, and squeeze one while spreading one. We already know the one spread out dries first before the squeezed one, because when it's spread out, the surface area is enlarged. It implies that all three things we're given were correct. The answer must be D. 1, 2, and 3. And with that, I'd like to tell you thank you again for watching this class. Please remember subscribe to this channel so as to enjoy more videos teaching you several more things, different topics, different subjects, different tutors, all brought to you by O3 Schools JAMB app, which you will need to get and activate to ensure your success in your examination. Thank you for watching. I am Kadiri Kame Athanasius.